Hello everyone, today we'll make a brief introduction about the modern surveying technologies, including the surveying with the GPS devices and LiDAR sensors. First, let's make a brief introduction about GPS surveying. Actually, nowadays GPS has been widely implemented. Your smartphones, the GPS navigation system, and even some modern car models are involved with some GPS chips. Here, GPS actually stands for the Global Positioning System. It will use an array of the satellites to calculate location of any point on the Earth. With this system, we can identify the latitude, longitude, and elevation of any point. Currently, there are 4 mature GPS systems applied in the world. Most of them are using 2 arrays to identify the location on the Earth. The first one was developed by US in 1993, which is the GPS system, and this system contains 31 satellites. 24 of them are always activated. The second one, GLONASS, was developed by Russia in 2011. It also contains 24 activated satellites. The third one, Galileo, was developed by Europe in 2016. It contains 30 satellites and 24 of them are activated. In 2020, China developed the Beidou system, which will use 35 satellites. In this system, it actually applies 3 arrays to identify the locations on the Earth. India is also working on developing its own GPS system, which is called the Navy IC, and it's still on the development. All the GPS systems have 3 segments. The first one is the space segment, which are the satellites in the space. The second one is the control segment, which are the stations located on the Earth, including the master stations, monitor stations, and the ground antennas. And they will be applied to adjust the signals collected from the satellites. And the last one is the user segment, which is applied in the user end to identify the location of each user. The control segment is applied to improve the accuracy of the GPS locations. Take the example of the US GPS system. The master control station is located in Colorado, and also it has 5 monitor stations and 4 ground antennas located across the world to further improve the accuracy of the locations. The figure here shows the space segment of the GPS system, which are the satellites in the space. In this figure, you can see that the orbits of the satellites are not overlapped with each other, with that they are able to cover all the locations on the Earth. The user segment of the GPS system will refer to the users with the GPS chips to identify their own locations. And with this kind of chips, we are able to use the GPS system for military, search and rescue tasks, disaster relief, surveying, marine, aeronautical, and terrestrial navigation, remote controlled vehicles and robot guidance, satellite positioning and tracking, shipping, GIS, and recreation. The primary function of GPS system is measuring the position and coordinates of any points on the Earth. It can also be applied to measure the distance and direction between any 2 points. In addition, by tracking the movement of one point, the GPS system can also record the travel progress report. Moreover, the clock in the GPS system is very accurate, which means that we can use the GPS system for the accurate time measurement. In the development of the GPS system, the 24 satellites are assigned into 6 distinct planes, which is shown in the figure on the right. In each plane, there are 4 satellites and they are orbiting at approximately 20,000 kilometers above the Earth. With this kind of satellite arrays, they are able to cover all the locations on the Earth. There are actually some reasons for us to develop the GPS system with the satellite array defined in the previous page. Actually, we need at least 4 satellites in one array to get the precise latitude, longitude, and elevation of one point on the Earth. In addition, the 6 distinct planes are designed to make sure that if any two of the satellites will suffer malfunction or damage, then the system can still use the rest 24 satellites to find out an accurate location of any point on the Earth. The GPS system is actually using the lightning analogy to determine the distance from the user to the satellite. Actually, in the GPS system, we will use the code measurement to determine the distance. In that system, each satellite is transmitting a unique code, and the receiver has an almanac of each satellite, and it knows what code is transmitting at what time. So when a receiver receives a piece of the code, it knows exactly when the satellite transmitted the code, and then we will compare the current time with the time that the satellite sent the code, using the time lag to calculate the distance from the user to the satellite. The figure here shows the example about the code. The one below is generated by the satellite and is also known by the GPS devices. The one above is received by the receiver. By comparing these two codes, we can find out the time difference, which is also the time lag. In that sense, the distance between the user and the satellite will be the time times the speed of the light. And usually we set the speed of the light as 300 million meters per second. By measuring the distance from the user to several satellites, we can then use the intersection of spheres to identify the exact location of one point on the Earth. Usually we have to find out 4 satellites to identify a unique point on the Earth. Now let's see why we need to have 4 satellites to identify one location on the Earth. First of all, if we know the distance from the user to one satellite, then we can identify the location of the user to the surface of the sphere. And the radius of the sphere is the distance from the user to the satellite. And the center of the sphere is the satellite. If you also know the distance to the second satellite, as shown in this figure, the radius is 11,000 miles, then you should belong to the 2 spheres for the satellite 1 and satellite 2. And in that sense, you must locate it to the intersection of these 2 spheres. In this case, this would be a circle. With 2 satellites, we know that the user is located at one circle, and there are infinite number of the points along that circle, so still we cannot identify the exact location of that user. In that sense, we have to introduce the third one. If we know the distance to the third satellite is 11,500 miles, then we can get a third sphere, and this one will also intersect with the 2 spheres from 1 and 2. In that sense, you will find 2 intersections on the circle defined by the satellite 1 and satellite 2. These 2 points will be the 2 possible locations of the user. So the third satellite will narrow the possibility to 2 points. With that, we still need to introduce the 4th satellite to determine which of the 2 points is the location of the user. But this function is not very important for the 4th satellite. Actually, from the previous 3 satellites, we can easily identify 2 points, and these 2 points are usually very far away to each other. It will be very easy for the user to identify which one it has to take. However, in the GPS system, we observe some clock errors between the receiver and the satellite. The 4th satellite will help us to correct these clock errors In that sense, it can help us to improve the accuracy of the location. And that's the major function of the fourth satellite. In the GPS system, the clock errors refer to the difference in exact time between the satellite and the receiver. Actually, the satellite and receiver applies different type of the clocks. Usually, the satellite is equipped with an atomic clock with a precision of 1 nanosecond, while most receivers are equipped with the less precise quartz clock. The reason is like the atomic clock is very expensive. Usually it's around $50,000 to $100,000. Due to the less precision of the receiver clock, we will have some uncertainty in the reading of the time lags. This will cause some errors about the distance estimation. In that sense, we need to introduce the fourth satellite to reduce this error. If the receiver's clock were perfect, then all satellite ranges would intersect at a single point, but in reality this is not always true. With imperfect clocks, a false measurement will typically not intersect with the first three. In that sense, the GPS devices will be realize that there must be some discrepancy in the measurement, and it will try to synchronize with the universal time. To do that, the receiver will look for a single correction for the time measurement and subtract the offset to make sure that the intersection will converge to a single point. The correction procedure is called refinement, and this can be done by measuring the location of one point with the GPS during certain time. The figure here shows one example about the refinement, where we measure the location of one point with GPS for 24 hours. You can see that the GPS location will be deviated around the center, which is the true location of the point. Also, usually the accuracy of the GPS will be within 5 meters. In the real surveying tasks, we can actually apply the relative positioning method to improve the accuracy of the GPS devices. In this method, we will apply two GPS receivers. One receiver is set at no position, where we know the latitude, longitude, and elevation. The other one is roaming for the surveying tasks. When we do the measurement, we will make a simultaneous reading about the two receivers, and then measure the relative distance between these two receivers. With that, we can reduce the potential errors caused by the GPS devices. The figure here demonstrates the procedure of the relative positioning method. We have two locations. One is the fixed location where we know the longitude, latitude, and elevation. The other one is the roaming receiver where we will set the receiver at the location we want to measure. With the fixed receiver, we can use the GPS reading in real time and compare it with the known position to find out the error. And this error will then be applied for the roaming receiver and adjust the reading from the roaming receiver to identify the estimated accurate location of the point we want to measure. There are various types of the errors in the GPS surveying. We have already introduced the clock errors. The second type of error comes from the Earth's atmosphere. Usually the signals tend to slow down and refract as they travel through the Earth's atmosphere. In that sense, the time lag will not be accurate, which will cause some errors for the GPS measurement. In addition, the poor geometric distribution of the satellite on the sky can also cause some errors. But this error can be corrected by tracking more than 4 satellites. Moreover, the error can come from the satellite's orbits, which is caused by the space disturbance or the errors in the control software. Currently, we have the wide area augmentation system was applied to improve the accuracy of the GPS devices. This system will utilize the relative positioning method to improve the accuracy. Well, the fixed point is now set as the station for that system, and it can provide the accurate information about one fixed point, and this one will communicate with your GPS devices to improve the accuracy of your current position when you are roaming on the road. The figure here shows the distributions of the stations applied for the watch system in North America. You are actually referred to those reference points to improve your position when you are traveling in Canada and the US. As we showed previously, if we don't apply any correction for the GPS devices, then the error would be around 5 meters. This might not be appropriate for the route surveying and navigation system. Once the watch system is applied, we can see that the error could be reduced to 1 meter. This will be sufficient for most of the route surveying tasks and navigation systems. The watch is a service provided by FAA. There are also some other similar service providers. CORS is a similar service offered by the National Geodetic Survey. In Canada, we have the Canadian Active Control System to improve the accuracy of the GPS surveying. There are a lot of commercial civilian GPS devices such as Garmin GPS and low-end handheld GPS devices, which is applied in our lab experiments. Currently, most of GPS receivers can access to both GPS and GLONASS satellites, but this cannot improve the accuracy a lot. If the GPS receiver can track many satellites simultaneously, such as 5 to 12 satellites at once, then we can see a huge improvement about the accuracy. Usually with more satellites, there would be more redundancy and the accuracy would be higher. The table here shows some typical accuracy about different types of the GPS measurement methods. If we are only using the single GPS unit, the accuracy is around 1 to 2 meters. If we apply the relative positioning method, the accuracy can be improved to 0.2 to 1 meter. If we consider the surveying grid receiver with the relative positioning, then the accuracy could be improved to 5 to 15 millimeters. In addition to GPS measurement, recently some modern measurement technologies such as LiDAR and radar becomes very popular. The first one, radar, was developed by several nations in the period before and during World War II, and the radar actually indicates the radio detection and ranging. LiDAR is a new technology developed recently. It represents the light detection and ranging system as an active remote sensing technology. The LiDAR system will actually send out the LiDAR pulse from the source, and the time it takes from the light to return is applied for the estimation of the distance. And this one is quite similar to the total station. We will use the time of the flight to estimate the distance, where the distance is the speed of the light times the time divided by 2. Also, the LiDAR system will send thousands of pulses per second to determine the points at various distances and locations around the user. There are two types of LiDAR system, the stationary LiDAR and the moving LiDAR. The stationary LiDAR is usually mounted on a tripod, which the LiDAR sensor rotates 360 degrees around. The pulse laser beam is reflected from the objects such as the building fronts, lampposts, vegetation, cars, and even people. Then the return pulse are recorded and the distance between the sensor and objects are calculated. And the data produced in the point cloud format, which is a 3D array of points, each having the x, y, and z locations relative to a chosen coordinate system. The figure here shows one example about the point cloud generated by the stationary LiDAR system. With the point cloud, you can observe the sketch of the objects around the LiDAR. This figure shows another example about the point cloud from the stationary LiDAR system. Currently, most of the LiDAR system can send out 50,000 to 300,000 parts per second. This indicates that at every second, the system has to store 100,000 data points with X, Y, and Z position, and the size of data could be at a scale of terabytes. Moreover, some surveying with the LiDAR requires the specialized equipment. Usually, this will need to be contracted out to a company specializing in this area. It indicates that the cost of the surveying would be very high. Moreover, for most of the surveying with the LiDAR system, we have to set up the GPS receiver to establish the base station. However, there will be some benefit for us to introduce the LiDAR system. Usually, the accuracy of the LiDAR system is very high. The absolute accuracy could be around 5 to 10 centimeters. The relative accuracy could be even higher. This indicates that it could provide a very accurate surveying for most of the tasks. The second type of LiDAR is the moving LiDAR system, which is placed on the moving object. And this system should work with an internal measurement unit. Usually, this unit will measure the pitch, roll, and yaw of the area of the moving equipment. The figure below shows the definition of the pitch, roll, and yaw for the drone. Basically, it will show the rotations at different directions. For a moving LiDAR sensor that is mounted on a mobile platform such as satellite, airplane, or automobile, it's necessary to determine the absolute position and the orientation of the sensor to retain usable data. Also, the GPS provides accurate geographic information regarding to the position of the sensor, and an internal measurement unit will record the precise orientation of the sensor at the location. And these two devices will provide a method for translating the sensor data into a static point. Then we can use this information for various purposes. One of the popular implementations of the moving LiDAR is for the autonomous vehicles, where it's able to identify the surrounding vehicles and pedestrians in real time on a moving object. The figure here shows one example about the moving LiDAR system where the LiDAR is placed behind the airplane, and the airplane is also equipped with the IMU and the GPS devices, which are applied to identify the location and rotation of the airplane in real time. And the LiDAR will be used to scan the terrain on the Earth. The LiDAR system can be applied for a lot of areas. For civil engineers, we can use LiDAR system to conduct build surveying. They can also be used to monitor the structural conditions of the building and conduct the construction quality control. Also, they can be applied for mining and forestry. So that's all about lecture today. Thank you very much for your attention. With that, we have finished all the topics in this class, and I really appreciate all the effort you spent this term. In the next lecture, we will have a live session to review the final exam.